So today we're going to take a look at section 1.5. What we're looking at in this section is called infinite limits. And there's going to be a little bit of it that's going to feel like something you've done before. So we're going to start with that piece of information. Infinite limits are defined the following way. We're going to let f be a function. It's defined at every real number in some open interval containing c, except possibly at c itself. The statement, the limit as x approaches c of f of x is equal to infinity, means that for each m greater than 0, there exists a delta greater than 0, such that f of x is greater than m whenever x minus c, the absolute value of that, is between 0 and delta. A similar statement can be made for each n less than 0. There will be a picture. Right now, just jot down the verbiage. Okay, have you seen something like this before? Okay, nodding the heads is good. I'm not going to ask you to say it, but have you seen it? I hope the answer is yes. You saw this back in section 1.2. It didn't look exactly like this, obviously. This is something a little bit different, but there's a lot of similarities. In particular, the parts that should look familiar are these. That looks exactly the same. That delta itself showed up. And there's a good reason for that. This whole chapter, in chapter 1, is about limits. It's about getting really close to a value and seeing what happens, right? So the picture that we're going to have that's going to go with this looks something like this. Oh, let me get the right tool up. And the possible c value that it's referencing is right here. So if you were to describe what seems to be happening at c, what would you say?
Looks like an asymptote.
It looks like an asymptote, a vertical one, right? It looks like there's a vertical line that we're getting really close to, and obviously we're not touching it, right? But that's what it seems to be happening in this picture. And in particular, the description of the delta are talking about values that are really close to c. And they're saying if I get really, really close to c, that I'm going to exceed whatever the maximum was that I said I was going to be at. So we'll call this m right here. So there's some sort of leveling place for m, that if we get close enough to c around that little red region, we're going to be higher than that m value on the y-axis. And if we aren't close enough yet, we can just make it closer, right? If we can get closer and closer, we're going to get higher and higher on this graph, and we're going to exceed the m value that's there. And when that happens, we call that limit infinity. And we can't treat infinity like a number because it isn't. Infinity is not a number. Infinity is this concept of getting bigger and bigger and bigger forever, right? So that's why we're going to treat it a little bit differently. So there's a note here. Be sure that you see that this equal sign in the statement, the limit as x approaches c of f of x equals infinity, does not mean that the limit exists. This limit does not exist. On the contrary, it tells you how the limit fails to exist by denoting the unbounded behavior, right? It's without bound, it's exceeded. It's an unbounded behavior of our function as we get infinitely close to the value of f of c. We get infinitely close to the value of c. Okay, so infinity is not a number, right? When we say it equals infinity, we're not actually saying it equals that number. We're telling how it fails to exist. It fails to exist in a very specific way. So we're going to look at some examples about how that works. Okay, is everybody good with me moving from the screen? We're all good? Cool. Okay, so here's our first example. This says to determine whether f of x approaches infinity or negative infinity as x approaches 4, and it specifically says from the left, and then it says from the right. So we have two different things we're going to be addressing. We're going to look at this from a couple of different perspectives. The perspectives we're going to look at this from are a graph. We'll start with that one since I showed you already a graph. And then we're going to look at from a numerical perspective or a table. Okay? Because you can do this in either of those ways. Now notice, if you're thinking about from the left and from the right, that's what we did in section 1.4, right? In section 1.4, we talked about continuity and we talked about one-sided limits. What happens if we're approaching from the left? What happens when we're approaching from the right? And at least in my class, we talked about the day before, so back on Monday, that if you try to plug in 4, from an algebraic perspective here, we get a 0 in the denominator, and there's no way to reduce that or cancel out the zeros, so to speak. There's no way to do that. So we can't approach this from an algebraic perspective. Remember, there's 3 ways to approach limits: graphical, numerical, and algebraic. And algebraic doesn't work here because it can't put the number 4 in. That's why we're back to 2 options. So we're going to look at a graph first. If you have your calculator, you're welcome to get it out. If you don't, that's fine. I'm going to show you roughly what it looks like on the screen here anyway. The x value of 4 does produce a vertical asymptote over here. So this is at 4. And on either side, it looks something like this. And there's 2 things we're asked to find. We're asked to find the limit as x approaches 4 from the left of our function f of x. And we're asked to find the limit as x approaches 4 from the right of f of x. And so in some sense, I'm going to call this option A, right? It's the graphical approach to doing that. Okay, we talked about graphical limits. We did that back in section 1.2. And when we looked at these graphical limits, we talked about the fact that this is from the right side is from the positive over here. From the left is the negative over here, right? Positive and negative on the graph, on the x-axis. So if we're approaching from the left side, from 4 from the left, 4 negative, we're approaching from over here, right? And we have to be on the curve. So you're on the curve itself, not on the axes, not anywhere else in the coordinate plane, but on the curve. And what's happening as you do that over here is that you're going up, correct? Moving from the left toward the x value of 4, you're moving upward. And the question is, from the directions, does that approach positive or negative infinity? Positive infinity, right? It's the top part of the graph. In a very real sense, we've got the positive and the negative on here for the y-axis, just like we had for the x-axis. This approaches positive infinity. So let's say for a moment that you had a question that asked this, but it only asked for one of them, right? It didn't ask for from the left and from the right. It just said from the left. Or maybe it even asked it in this way. Like it didn't use words, it actually asked it for it in the notation. How would you justify that you did this? Well, if you were doing it from a graphical approach, you'd draw the graph, right? After you see it in your calculator, you'd draw the graph on your paper, and then you'd actually show that it's this part of the graph that you're looking at in some way. Whether you've done little arrows, whether you've drawn a circle around it, that you're identifying that this is the part of the graph that you're looking at. Does that make sense? Okay? So then, in fact, I'll draw it in red so that it matches. All my colors are going to match. We're going to do the other one. It says x approaches 4 from the right. Yeah? So if we're looking from the right, we'll use blue. We're coming from this side, and we're going toward x equal 4. X equal 4 is where I've drawn in my vertical asymptote here, right? It's the blue part of the graph. What is that one approaching? Negative infinity, right? It's plummeting down. And I didn't make a big mention of it. It was in the notation. It said that there's an n equivalent here for this. I could take the same graph, just flip it upside down, and we use n as the lower bound, and it would be decreasing even further than n. So just take this picture and mirror image it down, and you'd have the picture that we're talking about on the graph that we're at now on the blue part, okay? So it was there. We just didn't draw a picture for it. So on this one, it's negative infinity. And again, how would you justify that if you were asked for one piece versus the other? You would identify it by drawing the arrows or by circling the portion of the graph that you're looking at if you're doing it from a graphical perspective. Okay, does that make sense? Everybody's good with that? Okay, so this is graphical approach. Sometimes on tests, we like to say specifically, do it from a graphical approach, right? We want to see that you know how to use the graph. Sometimes we say, do it from a numerical approach. Do it from a numerical approach. And sometimes you get to pick. So I'm showing you both options because, again, you may be asked for one specific one, or you may be asked that you get, or told that you get to choose, or not told which one to choose, and then you get to pick and you can pick your favorite. This is the graphical approach. So we're going to do sort of part B, a numerical approach. Remember, anytime you see numerical, it means table. And we're going to do two tables, one from the left and one from the right. And this is going to look a lot like what we've done before with your calculator. So go ahead and grab your calculator out. And we're going to do the left side first. So first we're going to look as the limit as x approaches from the left of f of x. And this is the table that would support that we're going to write down next. So we have our x values on the left, we'll have our y values on the right. And we want numbers that get infinitely close to 4, but they're coming from the left-hand side. So what values would be getting close to 4, but they're smaller? 3.9. Yep. Okay, I'm trying to make this a little bit bigger so I'd have more space to write. Yep, 3.9. What's next? 3.99. And we'd have at least one more at 3.999. Okay, we're going to see if I can get the document camera to work since we have it in this room. These are pushed. People pull out cords and things don't always work. That one goes too. Has Dr. Marsh used the document camera in here? No. Okay. So it's not going to anything. I have a feeling it's not going to work. If it's not going to work, it's okay, but I'm going to try one more time just in case. Oh, how nice. That's a terrible image of it, but one extreme to the other. It's terrible. Any better than it was before. F. can just get it to have only this much of it there for the work. Can you see it enough? I think that's my best viewing so far anyway, yes? Okay, we're gonna hold tight and go with that. So put the equation in here. Our equation is -1 over x minus 4. You guys, probably most of you have better operating systems and it actually looks like a fraction, that's fine. Our window, right here, if we click on our window, just the -10 to 10 window, or you can go by Zoom 6 and it'll put it in a normal standard window. This is the graph that we drew before. That should have looked like your graph. Did it do that? More or less? Okay. And then did Dr. Marsh have you set up your table ever? Yeses? Okay, good. So right now, my table looks like this. It has some stuff in it from a previous class, and I'm going to delete it out. You should have the ability to enter X, and it should have a column that says Y1. Does anybody's calculator not say that? Okay, so we should be able to put in our 3.9, 3.99, and 3.999. Excellent. And the values it gives us are 10, 100, and 1,000. We don't even have to go over to them to see what they are. And then if we go back to my other screen, as we're going down this table, these values are approaching infinity. Good news, infinity. Okay, so again, if it only asked for the left-hand limit, this is the only table we would put. Okay, if you put two tables on there, it means you don't know what you're doing, basically. Okay, I want to know that you actually know that this is the table that we're looking at for approaching 4 from the left. This one, and gets the value of infinity. And we're going to do the same thing from the right because we are asked to do both in this particular one. So this is our left one. And then we have the limit as x approaches 4 from the right on f of x. And we have x, we have y. Now we need values that are slightly bigger than 4. What would those be? 4.1, 4.01, and 4.001. And if we go back to our calculator, I'm going to put those in, 4.1, 4.01, and 4.001. And nicely enough and sure, in fact, we see -10, -100, and -1,000. The two tables that I just created are reflections of each other. So one of them's got all the positives, one of them's got all the negatives, the numbers match. That doesn't always happen. That just depends on the equation you're working with. However, this table, as we go down this table now, does in fact approach the value we anticipated from our graph, which is negative infinity, right? Kind of cram down there in the bottom corner. But okay, so two approaches, graphical, numerical, for this particular problem. Any questions on that? Okay, so let's talk about one of the things that we've already encountered now, which is vertical asymptotes. So you know from previous classes, at least Algebra 2, what a vertical asymptote is. It's that vertical dotted line that I drew in there. It's not drawn on your calculator, right? Your calculator does not fill that in because it's actually something that we recognize as something we are not going to get close to. It's not a part of the actual graph. It's a bounding feature. As f of x approaches infinity or negative infinity, as x approaches c from the right or from the left, then the line x equals c is a vertical asymptote of the graph of f. It's called a vertical asymptote. And then we've got a theorem about vertical asymptotes that follows. Theorem 1.14 says the following. If we have two functions that are continuous, f and g, on an open interval containing c, f of c is not equal to 0, g of c is equal to 0. Okay, so if you look down here how we're defining it, they're telling you that the numerator is not 0 and the denominator is. That's sort of the backwards way of how we've said a lot of our other limit theorems. Yeah? Okay, so we're talking about what happens when the denominator is 0 but the numerator is not. Then for all x that are not equal to c in the interval, this rational function f of c over f of x over g of x has a vertical asymptote at that x equals c value. Okay, so back in section 1.3, the majority of what we saw happen when we tried to algebraically plug a number in for x was we got a 0 on the top and a 0 on the bottom. Shake your head if you remember that. Okay, and we learned several ways to deal with 0 over 0. One of them was factoring, right? One of them were trig substitutions, right? When it involved trig, right? Tangent, changing it to sine over cosine, things like that, and trying to eliminate things. And one of them was rational functions where we multiplied by conjugates. Those were the three approaches we had. But in every case, we talked about the fact that it's only necessary and it will only work if 0 over 0 is what's happening, right? That's not what's happening here. I'm not getting 0 over 0. I'm getting some other number over 0. So when I get some other number over 0, I'm going to get a vertical asymptote. And in particular, I'm not going to be able to factor something out and cancel it. Like that won't work to actually solve the problem, which is why this is coming up. So we're going to find the vertical asymptotes if we have any of these functions. This is our first one, number 2. X squared minus 9 over x squared minus 2x minus 3. Okay, so vertical asymptotes happen when I don't have factoring that cancels things. So if I'm looking for the vertical asymptotes, what it means is that I'm back to trying to figure out what's going to factor and cancel out, and I'm going to be left with the other piece, and that's going to be my vertical asymptote, or at least create it. So I'm back at the point on this problem, much like I was in section 1.3, where I'm trying to factor and cancel things, but for a slightly different purpose. So how does that numerator factor? Yes, x plus 3x minus 3. Does anyone know what that's called? Difference of squares. This is the bane of my children's existence right now. I have children who are in Algebra 1, 3 of them, in Algebra 1 right now. And they're doing factoring. And every time I get difference of squares, I get this glazed look on their face. And I'm like, this is one of the easiest ones. Why are we so frustrated about difference of squares? Okay, so it's the good ones, right? The first piece squared, second piece squared, put a sign that's different in the middle. They're the good ones. Easy. All right, the denominator, still not terribly difficult, but it's not difference of squares. How will the denominator factor? X minus something and x plus something. Okay. Yep, 3 and 1. X minus 3 and x minus 1. Now, I had mentioned when I taught this that in 1.3 that you should anticipate something's going to cancel out. Like that's the expectation here, right? We expect that to happen. So if you're finding things are not canceling out, just double check your factoring before you assume that it's right? Because probably there's supposed to be something that cancels out. And sure enough, something does. What cancels here? Yeah, the x minus 3s. And when we saw this happen inside of section 1.3, we talked about, at least in my section, that what was being created in the graph was a hole in the graph, right? That's actually an algebra idea as well. But what remains is creating my asymptote. So what remains at this point, on top is x plus 3 and on bottom is x plus 1. So what value on the bottom would create the entire denominator to be 0? What would I get for x that would create a 0 down there? Minus 1 or negative 1, right? X equals negative 1. So in particular, if you go back to the original equation and you attempt to plug in negative 1, you will not get 0 on top, and you will get 0 on bottom. Can you visually check that? I don't really care what I get on top, but you're not getting 0, correct? Right, you're not getting 0 on top, and you are getting 0 on the bottom. That's what puts it into this case. Do not have 0 on top, do have 0 on bottom. I've got an asymptote there. right? It didn't cancel out. So when I'm looking at what's going on here, my vertical asymptote for this one is the equation, and it is an equation. Okay, so if you tell WebAssign, it asks you what the vertical asymptote is, and you just tell it -1, it is not going to accept that answer. -1 is not an asymptote, it's a number. X equals -1, the equation of a line, could be the equation of the asymptote. Okay, so make sure you're putting it in as X equals. The vertical asymptote here is at X equal -1. Okay, so one of the things that you guys did on Wednesday is you talked about two different kinds of discontinuities. Do you remember what they were? Removable and non-removable, okay? Removable and non-removable. So taking a look at what just happened here, the non-removable discontinuity is the asymptote that we got, right? X equal -1. The removable discontinuity is the part that canceled out. It was able to be removed when we did that. So then moving into into the next direction set, deciding if it has a vertical asymptote or a removable discontinuity is really just an extension of what you just did in section 1.4 and what we did in that last problem. We're trying to decide, can I factor it? If I can, does it cancel? If it does, it's removable. If it doesn't, I've got an asymptote. So taking a look at this one, what do you notice about this function? Do you see the discontinuity at X equal -1? Yeah. Okay, anytime you make the denominator 0, there's a discontinuity. There's a discontinuity there. What kind is it? It's an asymptote, right? Why can't it be removed from an algebra perspective?
Because you can't simplify that at all.
Right. I can't simplify this expression at all. In fact, the numerator doesn't factor. Right? If it said x squared -1, it would. Agreed? It'd factor anyway. But x squared plus 1 doesn't even factor. So I don't even stand a chance at reducing something in the denominator, whether it reduced the right thing or the wrong thing. I just can't even reduce it at all. So since I can't reduce this, I can't remove anything. So this means that x equals -1 is an asymptote because the x plus 1 on bottom will not reduce, we'll use the word that you guys used, reduce with any factor on top. I'll say in the numerator. Does that make sense? Just a slight extension from what you did in section 1.4 is all that is. Just a slight extension. All right, so let's take a look at some properties of infinite limits. And they're kind of what you would expect them to be, but infinity works a little bit weird, so we have to take a little bit more care with them than we do with numbers. Limits work really much, very much like you would expect them to work in general. These are limits that are infinities, so they feel a little bit odd. So C and L are real numbers. Okay, they're not infinity, they're numbers. F and G are functions such that the limit as x approaches C of f of x is infinity, and the limit as x approaches x approaches C of g of x is L. So you have one infinite limit and one finite limit. Okay? One of them is infinite, one of them is finite. And this talks about what happens when we do some operations with them. So in real sense, you're trying to multiply something that's getting infinitely large by something that's approaching a number. So if you think about multiplying infinity by a number, it should be infinite, right? It's infinity. So that's why you're seeing the infinity happen over here. Okay, you're basically multiplying something that's infinite by a finite number that's still creating an infinite quantity. The second one, it talks about the negative infinity. So if we're doing this and the limit is actually positive, it's infinity, and if the limit's negative, it's in negative infinity. Right? So if you multiply by a negative number, you're going to get negative infinity. I skipped the sum and difference ones. I'm so sorry. addition and subtraction. If you add and subtract infinity and a number, right? Infinity plus 5 is still infinity. Infinity minus 5 is still infinity. So that's the first one. That's the one I skipped, so sorry. And then we have the ones that we multiplied. The denominator one, the one that has the quotient in it, is the most interesting because it's not one we talked about. So this is telling you that if you have something on the top that's a constant, right? It's a number on top, and you're dividing it by something that's getting infinitely large, you get 0. So think about that with me. Let's just take a number 5. If you divide 5 by 10, you get 0.5 or 1/2, right? 5 by 10, that's easy. If you get 5 by 100, it's going to get smaller. And then if you divide 5 by 1,000, and then 5 by 10,000, then 5 by 100,000, then 5 by, right? As this continues to go, it gets smaller and smaller and smaller. It gets infinitely close to the number 0. So that's its limit. This is the one that takes a little bit of work to think through. The other two seem very clear. Similar properties hold for the one-sided limits for the function. So these are as x approaches c. We could do the same thing for x approaches c from the right or from the left. And also for what happens if f of x is actually approaching negative infinity instead of positive infinity. Similar or analogous statements would hold. Okay, so we have one more example. This is a one-sided limit, and I will let you guys see exactly what it would look like from two perspectives now, since I did it from 4 perspectives, kind of, on the first one. Oops, there we go. We're going to find the one-sided limit if it exists. Our limit is saying limit as x approaches 2 from the left of x squared over x squared minus 4. Okay, so what are our two options of ways to find this? Graphical and numerical. Those are our two choices. Okay, we're going to do it each direction. Okay, graphical. We're going to put it in the calculator and graph it. So we have x squared over x squared minus 4. You can do it in a standard window. This graph looks something like this. Your calculator, of course, is not putting in the dotted lines, but I will. Is that what your calculator shows? Approximately? Good. So there's definitely some asymptotes here. I could label my values. I could probably do that here real quick. This is 2, and this is at negative 2. Those vertical asymptotes there are. But this is why I mentioned before that you need to identify what part of the graph you're looking at. In a very real sense, you could get the right answer for a completely wrong reason. Correct? I need to make sure, Dr. Marsh would want to make sure that you're looking at the part of the graph that's actually applicable to this particular question. What does this say that we're supposed to be doing here? Approaching the value of 2, which means everything on this negative side of the graph is not what we're looking at, correct? And the little negative after the 2 means from the left. So the part of the graph that this is referring to is this portion of the graph. Do you see any other portions of the graph that are sort of doing the same thing? You do, right over here, right? This part of the graph over here which is not the part we're supposed to be looking at, will yield us the same answer. But if that's the reason that you're giving the answer that you're giving, you're not actually giving the right answer. You'll get the same answer, but it's not the right answer. Are you with me? So we want to make sure that you understand where you're at on the graph. This portion right here that I've circled is where we are on the graph. It's the value 2, but on the slightly left-hand side. What value are we approaching in this area of the graph? Negative infinity. So this limit, as x approaches 2 from the left, oh, it doesn't give it a name, so I'll just write it out, of x squared over x squared minus 4 is negative infinity. Okay, makes sense? Wonderful. So the other one we're going to do is numerical. Again, you may be told which one to use, or you may get to pick if you're choosing yourself, like if it's a choice you have, then it means we don't need to see both. You can verify both, that's fine. But we don't need to see both, okay, if it just asks you for one. So for a numerical approach, we're going to look at a table. And what values should be included or are reasonable to include in this table? 1.9. So often when I ask a question about one-sided limits, I still have people writing down two sides of a table. Again, that's not showing that you understand the question that's being asked. This question specifically says a one-sided limit as we're approaching the number 2 from the left. So slightly smaller than 2. 1.9, 1.99, 1.999. So let's let our table find those values for us. And I'll avoid putting it on the screen. It does what we call truncate the numbers in the column underneath y, which means it like stops them because there's only so much space. If you arrow over to the y1 column and actually put your cursor on the numbers, it will give you an expansion that's much more detailed. So we're going to write out 6 decimals. So I've got negative 9.256401,410. If I go down one, I have negative 99.250627 if I round. And the last one is negative 999.250063, I believe. Are those the numbers yours are showing up at? Okay, excellent. And again, we're looking at what happens as I go down this table. And as I go down this table, what value am I getting close to? Sorry, I'm writing out my notation. And you're right, it's negative infinity. Any questions on that?